This work presents the Surface Edge Explorer, a new approach to next best view planning. Models of real-world scenes can be obtained by combining individual observations from multiple views into a single 3D representation. The quality of these models depends on how well the observations capture the scene. The problem of selecting and planning sensor views to obtain high-resolution scene models is known as next best view planning. Existing next best view planning approaches often use either volumetric or surface representations. Volumetric representations discretize the scene into voxels. They typically do not scale to producing high-resolution models of large scenes. Surface representations estimate surface geometry from observations. These often require tuning of unintuitive parameters or multiple survey stages. The Surface Edge Explorer, or SEE, is a scene model-free approach to next best view planning that uses a density representation. This representation uses a given resolution and measurement density to define a frontier between fully observed and partially observed surfaces. Sensor views are proposed to observe this frontier until the entire scene is observed with the chosen resolution and measurement density. SEE works as follows. Frontiers are detected by classifying sensor measurements as either core, frontier, or outlier points based on the number of neighboring points. Potential views are proposed by estimating the local surface geometry around frontier points as a plane described by a set of orthogonal vectors. Views are proposed orthogonal to this locally estimated surface plane to maximize sensor coverage. The next best view is selected from these proposals to reduce the distance traveled by the sensor. Views that do not expand frontiers on discontinuous or highly non-planar surfaces can be adjusted. SEE continues to select next best views until there are no more frontier points remaining. SEE was evaluated in comparison with publicly available implementations of state-of-the-art volumetric approaches. We plan to include comparisons with surface-based approaches in future work. Experiments were performed in a simulation environment using a noisy depth sensor. Results show that SEE can observe scenes with greater surface coverage and in lower computational time. This video shows a time-synchronized comparison of SEE and the average entropy, or AE approach, running on a model of the Radcliffe camera in Oxford. AE was presented by Kriegel et al. In 2015, and the implementation used was published by Isler et al. In 2016. You can see that SEE completes observation of the model in less time than AE, while also obtaining higher surface coverage, although it does travel a further distance to do so. Thank you for listening. If you are interested in hearing more about SEE and our plans for future work, please visit us at our presentation stall.